this video, we're going to look at section 10.4. Section 10.4 looks at calculating type 2 error probabilities and finding sample sizes for z-test. So we're going to look at several examples. Some of these examples you've seen before, but we're just going to look at them with a little bit of a different context. So example 1 reads, a sociologist claims that the average number of people per family unit in a large subdivision is higher than the national average of 4.7. He interviews 100 families and obtains a mean of 4.8 with a standard deviation of 0.8. So first of all, notice that we've interviewed 100 families, so this is going to be our sample size. We've got a sample mean of 4.8, so that'll be the y bar, and then we've got a sample standard deviation of 0.8, so that is going to be our s, and then we're given that alpha is equal to 0.1. So the very first thing we're going to do is we're going to calculate beta for the alternative. And this is going to be a specific place in the alternative hypothesis. So to view that, let's first set up what our hypotheses are for this problem. So we're trying to prove that the population mean is greater than 4.7, and under the null, we're going to set the population mean equal to 4.7. So notice that the alternative is any value greater than 4.7, and 5 is greater than 4.7. So this is a specific place in the alternative. So whenever we calculate beta, we have to pick a specific place in the alternative. We could redo this example when beta is equal to 4.8 or 4.9 or 10 or 5.7, anything that's greater than 4.7 would be a valid option to calculate beta for, because we're going to look in the alternative hypothesis. So recall that beta is equal to the probability that we accept the null, or pardon me, let me start this again here. It's equal to the probability we accept the null, given that the alternative is true. And this given the alternative is true, that's why we have to pick a specific place in the alternative, because we're going to work under the assumption that the alternative is true, and so we need to pick a specific place in the alternative. And then recall, if we look at the rejection region, we reject HO if the z that we find is greater than 1.282. So what this tells us and I'm going to put this in quotation marks here because we know we don't actually accept the null. Really what we do is we fail to reject it. If z is less than or equal to 1.282, where z is equal to, and I'm just going to write down our formula, so in this case, under the null hypothesis, mu is equal to 4.7, so we have 4.7 here. All right, so we can use this information to help us write out what beta is. So again, remember that beta is equal to the probability that we accept the null. Well, the probability that we accept the null is when z is in this region. So this is going to be the probability that z is less than or equal to 1.282, given the alternative is true. And remember, we're looking at this specific place in the alternative hypothesis, so this will be that mu is equal to 5. Well, notice we know what z is equal to, so we can plug in the formula for z. So this is going to be equal to the probability that y bar minus 4.7 divided by sigma divided by the square root of n. so that's just the z, less than or equal to 1.282, and again given that mu is equal to 5. Well, looking at this probability statement, notice that y bar is the random piece here. So let's get y bar by itself. So this is equal to the probability that y bar minus 4.70 is less than or equal to 1.282 times sigma divided by the square root of n, again given that mu is equal to 5. And so this is equal to the probability that y bar is less than or equal to 4.70 plus 1.282 times sigma divided by the square root of n. And again, this is given that mu is equal to 5. Now we're given what the sample size is equal to. So since n is equal to 100, and we're going to approximate the population standard deviation with the sampled standard deviation. So we're going to assume that the population standard deviation is approximately equal to the sample standard deviation, which is equal to 0.80. We can fill those values in, and this is equal to the probability that y bar is less than or equal to 4.70 plus 1.282 times 0.80 divided by the square root of 100. And again, we're going to be given here that mu is equal to 5. And so this gives us that beta is equal to the probability that y bar is less than or equal to 4.8026, given that mu is equal to 5. Sorry, I paused there for a minute, and you'll notice I added on a couple parentheses because I realized that I was missing those at the end of the probability statements. All right, so I've ran out of room on this page, so I'm actually just going to pull out a blank piece of paper to finish this one. So notice that we know that beta is equal to this probability. Also, we know the sampling distribution of y bar, so we can find this probability. So since we're making the assumption that mu is equal to 5, we know that y bar is approximately normal, and it's going to have mean equal to 5. And then our variance is going to be equal to sigma squared divided by n. And recall that we know that z, which is equal to y bar minus 5, and again, the 5 here is because we're assuming we've made that assumption in our probability that mu is equal to 5. So this is different than the z we had up before, where we made the assumption that, under the null. So we've got y bar minus 5 divided by sigma divided by the square root of n is approximately normal. 0, 1, or standard normal. All right, so we can substitute in here to help us. So beta is equal to the probability. And so the first thing I'm going to do is I've got this probability statement right here. I'm going to convert the y bar to a z. So here on the left-hand side, you're going to see this piece right here. Well, if I convert y bar to the z, I have to convert the 4.8026 as well. So that's what I'm going to do on this side of the inequality. and then we're still given that mu is equal to 5. So this statement and this statement are exactly the same. The only difference is for this side and this side of the inequality, we're standardizing so that we're now going to have something that follows a standard normal here. So notice this is equal to the probability that z is less than or equal to 4.8026 minus 5. We're going to estimate the sigma with the 0.8, and then we have divided by the square root of 100. And at this point we can drop the given mu is equal to 5 because we've already incorporated that information here. So this becomes the probability that z is less than or equal to negative 2.468, and we can look that up on our calculator. So to find that on your calculator, we're going to go to second distribution. We're going to go to normal CDF. We want to get the value all the way from the left tail up to the endpoint. So here I have in basically negative infinity. My upper bound is going to be negative 2.468, and mu will be equal to 0 and sigma is equal to 1, again because I'm working with the standard normal here. That's why we converted over to the z. And this is going to give me 0.0068. And notice that is very small, so that is a good choice for beta. So in other words, beta is very low, which is what we would want in this case. Now, alternatively, we do not have to convert to the z. And so this is going to relate back to when we had options when working with the sampling distribution. We could either make the conversion to z, or we could work directly with the sampling distribution, and we can do the same thing here. So notice the whole reason that we made the conversion to z was because we wanted the following. We wanted beta was equal to the probability that y bar was less than or equal to 4.8026, given that mu is equal to 5. Well, if we're given that mu is equal to 5, we know that y bar is distributed normal with mu equal to, sorry, I should have said 0.5 there, this is just 5, mu equal to 5. And then our variance, remember, is sigma squared divided by n, or in other words, our variance, we're going to estimate it with the sample variance divided by, oh, there's no square root here, this is just 100, no square root. So that's our variance. Well, notice that the standard deviation of the sampling distribution that is going to be the square root of the variance, or in other words, that will be 0.8 divided by 10. So what we can do is now directly find the probability that y bar is less than this value. And to do that, what we do is in our calculator, again, we're going to use the normal CDF. We're still going to have the lower bound of negative infinity, but now we're going to work directly with the sampling distribution. So this is going to be our upper bound. Our mean for this normal distribution is 5, and our standard deviation is going to be this value here. So notice if we put that in to our calculator, we get pretty much the exact same answer. There's just a slight bit of rounding difference here from where we rounded oops, sorry, there we go, from where we rounded when we calculated z, but you get pretty much the exact same answer. So you can either make the conversion to z so you can work with the standard normal, or alternatively, what you can do is work directly with the sampling distribution, assuming that place in the alternative. But either way, you get the exact same answer. So for this section's quiz or assignment, whatever you want to call it, what I want you to do is I want you to rework this problem. But this time, I want you to, under the alternative hypothesis, I want you to move further into the alternative hypothesis to 5.2. So rework the problem. I want you to tell me what happens to beta. In other words, did beta get smaller? Did beta get larger? And whichever one you find, I'd like you to write just a sentence or two and talk about, well, why that would make sense for that to happen. So rework the problem, but have mu alpha, in other words, look at 5.2 in the alternative and see what happens to beta. All right. We've got another example here. This is on page 11. So page 11 reads, a real estate agent claims that at least 75% of retired couples prefer living in an apartment or a condo to owning their own home. Of 200 retired couples, 165 preferred living in an apartment or condo. And so we're going to calculate beta for the alternative of 0.79. So first of all, recall our hypotheses for this problem. Under the null, we've got p is equal to 0.75. Under the alternative, p is greater than 0.75. We're also given that n is equal to 200 and p hat is equal to 165 divided by 200. And again, we have that beta is equal to the probability that we accept HO. And remember, we use that language for these problems, but we really know that we don't accept the null. We fail to reject it. And then again, this is going to be given that HA is true. All right, so we're going to calculate this very similar to what we did for the previous problem. So first, let's recall what the rejection region is. So we reject HO if Z is greater than 1.645. So we accept HO if Z is less than or equal to 1.645. And recall that Z in this case is equal to P hat minus P naught divided by the square root of P naught times Q naught divided by N, which in this particular case is P hat minus 0.75 divided by the square root of 0.75 times 0.25 divided by 200. All right, so let's look at calculating beta. So again, beta is going to be equal to the probability we accept the null, or in other words, this is the probability that Z is less than or equal to 1.645, given the particular place in the alternative, which in this case is going to be P is equal to 0.79. Now we're going to write down what Z is equal to. So in this case, Z is equal to P hat minus 0.75 divided by the square root of 0.75 times 0.25 divided by 200. And so we're going to have that less than or equal to 1.645, again given that P is equal to 0.79. Now remember that in our probability statement, P hat is the random portion. So our next goal is that we want to get P hat by itself. So I'm going to skip a couple steps here, but I'd like you to try this on and confirm it. you should find that beta is equal to the probability that p hat is less than or equal to 0.8004, given that p is equal to 0.79. And again, this is getting p hat by itself on the left-hand side of the inequality. Now, since under the alternative p is equal to 0.79, we know if we look at the sampling distribution of p hat, we know that p hat is approximately normal. With, oops, that's an equal sign, p equal to 0.79, and the variance is going to be equal to p times q times n, and we're going to estimate p and q using p hat. So notice this is not the same as p and q under the null. This is different. Sorry, I misspoke here. P and Q are not coming from p hat. P and Q are what is true under the alternative. So this is different when we looked at P naught and Q naught up here. So this one is assuming the null is true. This one is assuming the alternative is true. So plugging these in, we're going to have 0.79 times 0.21, again divided by our sample size, which is 200, and that will give us the variance. So notice here that again, the variance of the sampling distribution, assuming that the alternative is true, is equal to 0.79 times 0.21 divided by 200. So the standard deviation of p hat is equal to the square root of this. So we can take 0.79 times 0.21 divided by 200. Take the square root of that. We're going to find that standard deviation is 0.02880. And next, we could do one of two things. To find this probability, we could transform p hat to a z. We could standardize it, and we'd have to standardize both sides of the inequality, and we could use a standard normal. Or we could find this probability directly from the sampling distribution of p hat, assuming that the alternative hypothesis is true. And so that's exactly what I'm going to do. So in this case, to find beta, what we're going to do is, again, I'm going to go to my calculator. I'm going to click on second distribution, normal CDF. Now this time I'm interested in the probability that p hat is less than 0.8004. So I'm still going to have the lower tail as negative infinity, but now my upper tail is going to be 0.8004. The mean of this sampling distribution, assuming that the alternative is true, is going to be 0.79. And then the standard deviation is the value that we found right here. Sorry, you can hear my dog squeaking on a squeaker toy. And here is the probability for this one. So beta in this case is equal to 0.641, which is fairly large for a beta. So if we wanted a smaller value of beta, we would need a larger sample size or an n, or a larger sample size or larger n. All right, so we have another example on the next page. You'll find this example is very similar. I'm not going to include this one in the notes, but I will write it up and post it on Blackboard so that you can see the solution for this one. And so this one will be very similar. The only difference will be is we're going to find the sample size if we specify a beta. So in this one, we're going to solve for n. So again, I'll write up the solution for this one, and if you have any questions, just let me know. And then there's a couple rules there at the very top of page 13 in terms of sample sizes. And there is one more example. I'm going to grade this one on completion. I will also write up a solution for it. But as a separate assignment, I'd like you to see if you can determine the sample size in for example 2. All right, so look over the solution that I'm going to post for page 12. See if you can come up with a solution for example 2. And again, what I'll do is I'll grade this on completion. You just try this. Once you submit it on Blackboard and you've given an attempt, the solution will automatically appear below. And so again, if you have any questions, please just let me know.